When you are preparing your sample for melting point, it's important to grind up your sample. You want to create a fine powder. I would recommend doing this with uh, a watch glass and a spatula as opposed to using a mortar and pestle, which is a traditional grinding tool. The mortar and pestle just has a large surface area, and it's going to be easy for you to lose a lot of your compound within the mortar and pestle. You're going to pack your fine powder into a melting point capillary tube that we'll have set out in the lab. And you want to get about 1 to 2 millimeters of sample in your capillary tube. You'll drop it down your long stem funnel to kind of pack the solid down. You don't want to pack your sample too tight, but you also don't want it too loose and have air holes within your sample. We do have some very long glass tubes that we can distribute throughout the lab in order to help you get better packing. They're much longer than your long stem funnels that can be inverted on the bench top. Finally, once you've created your packed capillary tube sample, you'll insert it into a melting apparatus. Our TAs for the labs have made a video showing you how to use the melting point apparatus that we have in the organic lab. So please see the link in our Moodle page and go to watch that video on YouTube. We do have instructions for setting up the melting point apparatus in lab, so you'll be able to refer to those written instructions as well. This is figure 3 from your lab book. It's showing some of the traditional melting point devices. A is the Thiel tube setup, which requires the use of a Bunsen burner, which is why we're not doing it this semester since we are all in flammable face mask. It's a very old technique, the oldest technique that they've reported here, and it takes advantage of the convection flow of heat, as we can see from the arrows indicated here. Traditionally, you put a Bunsen burner here and you're heating this oil that is surrounding your sample, and of course the heat causes the oil to flow due to convection, and that allows your sample to be nicely evenly exposed to a rising temperature. You can move the Bunsen burner closer or further from the apparatus to control the rate, which we'll discuss controlling the rate on our apparatus in a little bit. The other two examples that we see here are more modern versions of the Thiel tube and melting point devices, things that allow you to set rates and provide light bulbs that provide consistent heat, and also magnifying lenses to better be able to observe the melting point. Our current devices that we have in the lab are actually a little bit more modern than this device C, which is a Meltemp. Fun fact, that's what I used when I was taking organic chemistry. Ours are digital, so we don't have to interpret a thermometer. So when you are trying to identify an unknown particularly, you don't necessarily know what its melting point is. So you want to take what we call an orientation melting point and get an idea of your sample's melting point before you perform the mixture melting point that I discussed earlier. To do this, you're going to heat your sample quickly in what we call a fast rate of about 10 to 15 degrees C per minute. I recommend 10 degrees. It gets the job done quickly, but gives you a slightly more accurate reading. You want to heat it quickly until your sample melts, and you're still making these very careful observations, getting a melting point range, but because of how fast it's melting, your range is going to be a little inaccurate, okay? So it gives you a broad idea of what the melting point range should be. Once the melting point apparatus cools back down to 15 degrees C below the orientation melting point, that range that you had found in the previous step, using a newly prepared sample, you will now heat the sample slowly, and we call the slow rate about 1 to 2 degrees C per minute. Yes, this can take a while, but it gives you very accurate results. Heating slowly, you're going to accurately measure the melting point. So instead of saying, oh, well, the melting point was between 50 and 60 degrees, you'll be able to narrow that down within a couple of degrees of, for the range. Remember, heating slowly is the only way to get an accurate melting point range measurement. So, running an unknown sample, if you know the melting point of the sample, there's no need to do the quick reference, okay? You already know what melting point you're trying to aim for. This is the case in the first part of this week's lab. So what you will be doing is setting up your device and heating your sample quickly to within 15 degrees of its melting point. So you'll set a start temp 15 degrees below the known melting point, and at that point, the slow rate will kick in, and that slow rate of 1 to 2 degrees C per minute will continue until your sample melts and you restart your melting point and allow it to start cooling. This technique, being able to heat a sample quickly up to a certain point and then slow that rate, allows us to save time in the lab. Instead of starting out at room temperature and heating slowly 1 to 2 degrees C until we get to a melting point of benzoic acid around 120 degrees C, we can save time by quickly heating and just making sure to kind of slow down that rate once we get to be about 100 degrees C. Things to keep in mind considering potential errors. There can be a poor heat transfer rate, okay? This happens if you have too much sample, so if your sample size is too large, or if your particles are too coarse. You didn't get them ground up well enough, causing them to not pack well and leave air pockets that slow the heat transfers. Remember, air is an insulator, so it's not going to allow your melting point temperature to be accurate if there's lots of air pockets in your samples. As your compounds heat up, changes occur within the crystal structure prior to the crystals actually melting and turning into liquid. So you may see sagging or shrinking in your sample and mistakenly think that that is indicating that solid is turning into liquid, and that's not the case. Likewise, if your sample's not dry, this is more something to remember for future reference, but if there are traces of solvent due to the sample being wet or because it's absorbed some moisture in the air and is no longer truly dry, meaning totally devoid of solvent, then you may mistaken some droplets in the tube as liquid and your solid melting. A lot of times this looks like your sample is sweating, and that's not really the beginning of your melting. It's really just your solvent dissolving some of your material. So the thing to keep in mind when you're trying to identify the low point of your melting point, look for the first appearance of liquid within the bulk, the major part of the sample, not just sweating on the sides or up near the top. You want the first appearance of liquid within the bulk of the sample itself. And of course, your final reported value for the range is that temperature once the bulk is liquefied. So occasionally you might run into samples that sublime. That shouldn't be the case for today's lab since we're kind of training ourselves. But remember, sublimation is when a solid converts into a vapor without going through the liquid phase. If this is what's going on, what you will observe is the sample at the bottom of the tube that you're looking at through the magnifying lens, it vaporizes and actually will recrystallize higher up in the tube where it is cooler. We should not see that in our samples that we are analyzing this week.